Rotational dynamics is a unit of analogies. Linear and rotational motion are both defined in the same way, so each variable, law, and concept in rotational motion has an analog in translational motion that we've already seen. So, sit back and relax. You've seen this all before. Hopefully. In translational kinematics, an object's position is a point in space measured by its offset from the origin in the x and y directions. In rotational kinematics, the object's position is given by its angle off the horizontal and its distance from the origin along that angle. With this, we construct the universe. Angular displacement is the change in angular position, angular velocity is the change in angular displacement over time, and angular acceleration is the change in angular velocity over time. The new angular versions of our familiar quantities obey the familiar laws of kinematics. It's the same structure, just with different variables. The first new concept in this unit is that different points on the same object may move differently. As such, we'll often consider the behavior of particular points in rotating systems. A system is rigid when all points in the system rotate together, when every point has the same angular velocity and acceleration. Think solid objects. Rigid systems are well behaved. They can only move in limited, easy-to-model ways. If you want to learn more, Google linear algebra. Rotational motion happens when an object's direction changes continuously. The linear velocity of a point on a rotating object is its translational velocity in the current direction of motion. Different points in a rigid system may have different linear velocities. A point on the surface of the Earth moves faster than one near its center, for example. Some basic trigonometry reveals that linear velocity is equal to angular velocity times the distance from the axis of rotation, which is usually the system's center of mass. Points with different tangential speeds will travel different distances and accelerate at different rates. We find the same relationship between these quantities as well. But even when a rigid object rotates at a constant angular speed, the linear speeds of its points change direction, sweeping out a circle. Change in direction is change in velocity, which is, by definition, acceleration. Rotating objects always experience acceleration, even when their angular speeds are constant. Newton's first law tells us that acceleration can't occur without a net force. This net force is what prevents the object from being flung away from the center of the system. For orbiting satellites, this force is gravitation, but in other situations, it could be tension, friction, or the normal force. Inertia is a property of matter that describes how hard an object is to move. For linear motion, inertia is simply the object's mass, but for rotational motion, we also need to take into account the distance between the applied force and the object's axis of rotation. An object with mass m rotating at distance r around some point has rotational inertia mr squared. So, increasing an object's mass or its distance from its axis makes it harder to rotate. The total rotational inertia of a system is the sum of the rotational inertiae of its components, assuming they all rotate about the same axis. We've calculated rotational inertia for many common shapes. A system without external constraints wants to rotate about its center of mass because this requires the least energy. It figures that if we force an object to rotate around a different axis, we must expend more energy. The parallel axis theorem states that an object's rotational inertia about an axis parallel to one through its center of mass is its standard rotational inertia plus the mass times the square of the distance between the two axes. In order to cause angular acceleration in an object with angular mass, we need some sort of angular force. A torque is a force F exerted on a rotating system at distance r from its axis. Torque is equal to r times the applied component of F. So, torque increases when a stronger force is applied, or when the force is applied further from the object's axis. Conversely, we can exert a large torque with a small force by applying the force far from the axis of rotation. This is how levers work, although we often force the object's axis to be a particular point. Armed with rotational analogs for acceleration, mass, and force, we can interpret Newton's laws in rotational form. First, an object's rotational velocity remains constant unless an external torque acts on it. Thus, an object at rest can't begin rotating until a torque acts on it, and balanced torques sustain rotational equilibrium. Second, torque is equal to rotational inertia times rotational acceleration. Finally, every torque causes an equal and opposite countertorque. The core takeaway from this unit is that rotational motion operates much in the same way as linear motion. The variables may be different, but the relationships between those variables are the same. Both worlds exist independently, but there are bridges between them. We'll continue to see this in the next unit as well. If you want to learn more, Google linear algebra. Worst mistake of my life.